My great pleasure to welcome today's speaker, Professor Matias Zaldarriaga. Matias has done many groundbreaking and innovative research contributions, which has significantly enhanced our understanding of the Earth universe. So it began with his PhD work with Zaldarriaga on the development of a code, CMB-FAST, which was a game changer and foundational in CMB analysis. And their work on B-mode polarization in CMB from primordial gravitational waves has been one of the main motivations behind numerous CMB polarization experiments. So Matias has since continued to do many interesting and important works on fields such as 21 centimeter radiation, primordial non-Gaussianities, effective field theory of large-scale structures, etc., which has greatly impacted the research field, and also in particular has impacted and has been sources of inspiration for my own research work. Matias has won many awards for his work in those areas, with recent ones including Helen Warner Prize for Astronomy, Gribov Medal, MacArthur Fellowship, and in 2021, the Gruber Cosmology Prize, jointly with Seljak and Kamiankovsky, which states that they introduced numerous techniques for the study of the large-scale structure of the universe, as well as the properties of its first instant of existence. So today, Matias is going to tell us another interesting research area he studied recently, namely gravitational waves. Let's welcome Matias.
Well, thanks very much for the invitation. It's great to be back and see all these familiar faces. When I left here, my daughters were, the youngest one was just born, and now one of them will be going off to college, so it's just time goes fast, right? So anyhow, I want to tell you about some work that I've been doing on the gravitational wave background observed by the pulsar timing arrays. For those of you who know me know that this is not the thing that I've worked the most, so I'm happy to get feedback from you and stop me whenever you want, questions or comments. Great, so let's jump to it. A couple of introductory comments. So this is about the background of gravitational waves that has been detected by monitoring the pulses that arrive to us from pulsars in our galaxy. The pulsars arrive with a delay. If the universe is filled with gravitational waves, the pulsars arrive with a delay. There's two components to that delay. One, so when there are gravitational waves, these frequency changes of that leads to this delay have a part that has to do with gravitational waves at the source, at the pulsar, and some part that has to do about the gravitational waves at the Earth. All the pulsars on the sky share that Earth piece, which depends on also the direction of propagation of the gravitational wave relative to the direction to the pulsar. And as a result, all of those times delays should be correlated on the sky. And recently, these pulsar timing arrays that have been monitoring pulsars for decades have claimed to see an excess noise, an excess amount of changes in the delay arrival of these pulses on periods between 1 year and 10 years for these waves that are producing these delays, and that they are correlated on the sky as predicted if they're coming from a background of gravitational waves. For the purpose of this talk, I will take this at face value. I will assume that this is the interpretation of the measurements, and I'm just going to focus on what we can learn from astrophysically if these signatures are indeed produced by a background of gravitational waves. These are some of the plots of the nanograph papers that claim the detection. So they've measured an amplitude or energy density in this gravitational wave background as a function of frequency. That's an example in this plot, frequency of the gravitational waves, and the excess timing noise in the arrival of these pulsars. This plot shows a measurement of the correlation function of the time delays on between the separation of pulsars on the sky as a function of the separation of pulsars on the sky related to the fact that they all share this Earth contribution, and as a result, they are not independent, the delays that you expect. And so I'm going to take these things to be true and move on from there. So I know that the format is that the talk should be around 30 minutes, and so let me try to condense what I want to say at the beginning. I wasn't completely aware of this until recently, so let's just put the thing at the beginning, and I'll try to adjust the timing as I go along to fit these 30 minutes. So I'm going to discuss then the level of the background of these gravitational waves that one can interpret from these observations, and I want to make a connection between what are the sources, and there could be many sources for this background of gravitational waves, but the most natural source astrophysically is mergers of supermassive black holes. We know they exist. We know galaxies merge, and so probably the black holes merge. There's no need at the current time, I don't think, to think of, I don't know, some phase transition in the early universe. So for the purpose of this talk, the source of this background is the merger of supermassive black holes. And so I want to connect, I want to interpret the measurements in this way, and I will make the connection to see what one might expect with the local census of black holes around us in the local universe. And what I will try to convince you is that the background that is observed is a little bit on the high side. So its amplitude is a little bit high with what you might expect based on the local population of black holes. I'll tell you how that argument goes. I will also tell you that there's quite a bit of information in this frequency dependence of the background that might tell us about what's the mass of black holes that are producing this background, what's the most likely mass. And I'll maybe try to make some connection also with the type of Sultan argument of the black holes also being, the local black holes being at some point responsible for the quasars that we see at high energy. So that's the goal. And one thing that so this is work with Gabi Safapolito, who's a postdoc at the IIS, and Elliot Quattert, who many of you know very well. And the other thing that I want to mention is that most of these calculations that I will tell you about are just very simple analytical type calculations. These are completely things that you can put in some, exercise for some graduate course in cosmology or whatever. So I think the connection between the background of gravitational waves and the local population of black holes is pretty straightforward and pretty robust and easy to explain. So
Matias,
yeah.
Is it possible? When galaxies merge,
yes,
the two black holes very often come together, and
yes,
sometimes they get a recoil that
yes,
can remove the black hole
yes,
from the galaxy. So those are black holes you will not find in galaxies
yes,
today. So
yes,
that is a caveat to what you just said.
Let's keep that in mind. Of course, there could be black holes that we haven't, that don't live in the centers of galaxies, and then from this argument we will see what type of black holes are the ones that produce this background, and if you wanted to make this background, how many more you would need, and then we can decide if these, how many more floating black holes there should be. Of course. So, okay, so I want to discuss the amplitude of the spectrum and also the frequency information. So about the amplitude of the spectrum, this goes back to some very nice paper by Stern Finney. So it's a very simple argument. So let's just, the point of the initial part of the calculation, instead of trying to move forward and try to estimate mergers of galaxies and so on, let's start from the black holes that we observe. Let's assume that those black holes that we observe in the center of galaxies are the remnants of these mergers, okay? And so each of them could have merged or maybe didn't merge. Of course, if they didn't merge at all, they didn't produce any background. So in order for them to produce the background, they need to have merged. And so you might wonder how many times they merge, at what redshift. And so it would look like the connection between those remnant black holes and background that they could have produced through the mergers is kind of quite uncertain, because you don't know how many times they merge, at what redshift, and so on. It turns out it's not very model dependent, the connection, for the following reasons. So if you think about, so where the background, basically you need to understand the amount of energy in gravitational waves. This energy comes from the orbit of the black holes. And so you can easily calculate that energy and how it scales with the mass of the system and the separation of the black holes as they are spiraling in. Very important thing that if you estimate the amount, the background, how it depends, say, on the mass of the system, it depends like the mass to the 5/3 power. This means that if I have my black hole now, I emerge. It also, before I say, also you get the most energy out if it's an equal mass merger. If you merge with something very small, you don't get much out. And so, because we will be trying to get as much of a background as possible, it's a good estimate for the beginning to just think that you are merging something of similar mass. If not, you have to merge many more to get the same background. But so, if you think, let's just, for the purpose of the discussion, think that you have a black hole, it merged with somebody of the same mass, it merged again, it comes from some sort of tree. But each time, each leaf in this tree has smaller and smaller mass, and so it produces less and less background. And so most of the energy that you will get out is from the last merger. And you can even add up infinite number of mergers each time the two masses are half. This gives only a factor of 2 difference if you with just taking one merger of equal mass. So roughly that's the kind of uncertainty I will be referring to when I say it's pretty robust. Is that okay? There's some sort of factor of 2 that you don't know, because you don't know if it merged once or twice or. But it's not a big deal, because for the most part, the last merger is the dominant one. You could also think about at what redshift do I put the typical mergers, and this might make things very different, because there's a 1 plus z redshift of the energy as the universe expands. But the 1 plus z factor is not even 1 plus z, because if you put the for a given observed frequency of the gravitational wave, if you put the merger at a higher redshift, the emitted frequency had to be higher. And the efficiency with which a binary is emitting, the amount of energy it's putting out, increases when they are closer in. So that cancels 2/3 of the 1 plus z, and so it's only a 1 plus z to the 1/3 that you can play around by putting the binary at a different redshift. So 1 plus z to the 1/3, all of these things are happening, around redshift 1 or below, so it doesn't make much of a difference. So if you can, conclusion, if you can count the local population of black holes, you have a good estimate of the energy density on the background, which has some uncertainty within some sort of factor of 2, and you get this estimate by assuming that everybody merged once with somebody equal mass. Okay, I mean, you can do it more carefully, but for the purpose of the talk, it's good enough. And so then in order to know about this background, you might say, we need to count the local population of black holes and then put this into this formula. How do we do that? We know that the masses of black holes in galaxies correlate with the properties of galaxies. So, for example, here is the m-sigma relation. You can count galaxies as a function of sigma, use this relation, and estimate the density of black holes in the local universe. That's an exercise that people have been doing for quite a while. And okay, if you do that and you take the estimate that I told you before, what do you find? Well, you find that, so let me say a few things. You can estimate in this way the mass function of black holes in the local universe. Depends on the details, how exactly you do it, what exactly you get, how there's more than one version of the M sigma relation, or correlate with some other property, more than one version of the mass function of galaxies and so on. But if you do that, you get plausible mass functions for the black holes, which they all have some sort of very steep cutoff at high masses coming from the cutoff in the number of galaxies at high, say, velocity. And so the typical background that you get, the average background that you get, would be related to the number of black holes times the formulas that I said before, that basically the background being produced is proportional to the mass of the black holes to the 5/3 power. So if you see from what kind of masses you get the background for the typical mass functions that you estimate in this way, this is the kernel that tells you the fraction of the background, how is it being produced as a function of the mass of the black holes. And just to say that it's typically produced by black holes of a little bit above 10 to the 9 solar masses. Those are the ones that contribute the most. Much higher much higher masses, they're very rare, okay, so they don't produce much of a background. Much lower masses, they don't produce much background because they're not so heavy. Okay, so that's the situation. And roughly speaking, these are measurements of the background is really the square of this thing, the energy density. That's what's proportional to the number of black holes, is the hc square. And so the estimates that I just told you are around here. These are the measurements. So there is some sort of, in this amplitude, some sort of factor of 2 kind of difference with this upper limit. And in the types of, in the energy, it's the square of this, so there's a factor of 4. So if you wanted to make these points lie on top of here by increasing the number of black holes, you would need to increase the overall number density by a factor of 4. So that's the situation. So conclusion, better be that most of the black holes merge at least once so that we can get into the ballpark. Even if we do that, we are not really getting to the place, but we're not so far off. So most probably this is the source of the background, but it looks like there is a little bit of a discrepancy in the background as measured is on the high end of what you might have expected. So you might think, okay, if I wanted to make these two numbers agree better, what would I need to do? You can change the M sigma relation a little bit. You can change the number of galaxies that are out there, the given sigma. All of these things by factors of order a few, or that's what you would need. One thing that is I put this here to remind me to say is that these are the measurements of the M sigma relation. That's a power law scaling. Let's say there's some scatter to it. One thing to remember is that if you look at, let's say here, you might claim that most of the background is coming from black holes of masses a little bit above 10 to the 9. But where are those black holes from? So there's the line a few times 10 to the 9. So the ones sitting here, the galaxies are pretty rare. Okay, so they're not from these guys here. They are about more, it's dominated by outliers of the n sigma relation in more numerous galaxies. So the estimate of the background hidden inside is some belief that we understand this scatter, okay, which I'm not sure should be completely believed. So as an example here is just the cumulative distribution of the residuals of the m sigma relation in that plot, okay? And they're fit by a Gaussian, so people fit this by a Gaussian, they report like the width of the scatter in the m sigma relation. That is what's going into these predictions. And here is the cumulative distribution of where that background of gravitational waves is coming from. So 50% is coming from above these things, which are things that scatter above the m sigma relation by a factor of 4 or 5. Okay? So those, in terms of the scatter here, there's not anybody there, right? So it's just the extrapolation of the scatter that is doing like at least half of the background. So I think it's a little bit of a dangerous situation. Furthermore, you know, a lot of points are over here. These masses are not relevant. So the ones that we care about are guys at 10 to the 9 or something like that. There's not that many. So okay, take this with a grain of salt. So, but it also means that if you start mucking with the scatter and so on, you can change the prediction by quite a bit. And that's maybe a way around the problem. Okay, so conclusion, the background may seem a little bit high, but let me just go back to this measurement as a function of frequency. The PTAs give you some estimate of the background as a function of frequency. There is a very nice prediction for the average spectrum of the gravitational waves from binaries, which is a specific power law here that it's very robust, very model independent, because all that is happening, if you want to ask the question of what's the energy density in the background, this frequency versus that frequency versus some other frequency, the binaries both emit all of these frequencies as they spiral in. And the amount of energy available coming out in this frequency is just about the binding energy of Newtonian orbit. So as you change the frequency, you change the radius, so the slope is fixed by this, by the Kepler's law. There's not too much. So for the average, there's a particular spectrum there that you expect, and it doesn't really matter what mass of the black holes, the binaries there is, they always give the same, for the average. And so that's what typically people fit to this. But the average, and we don't observe the average, we observe the background in our realization of the sky, and it'll turn out that there's a lot of information in there for the reasons that. So let's try then to estimate the amount of power that you should see. What's the distribution of power that you see in different that you might see in different frequency bands? And keep in mind that even though a binary will eventually go through all of these frequency bands, the amount of time it spends in all of them is different. It's shorter as we go to higher frequencies. So you will get into a situation in which if you go to sufficiently high frequency bands, the chances that you catch one of them is becoming, especially a massive one, is becoming smaller and smaller. And so you might have many things contributed at low frequency and few things contributed on high frequency. And so the Poisson fluctuations might mean that it's, if you are thinking that the sources are sufficiently rare, you should see a lot of beams with no sources in the PTA results. So there might be a big difference between the average amount of power that you would expect to see and the power in a given realization that we should see in our universe at a given time. So this can be all computed pretty much by hand. You can think that there is some sort of luminosity function that gives you some sort of the number of black holes as a function of the strain that they are emitting. And you can try to, the total power on the sky is the sum over a bunch of sources. You don't know how many sources there are. There's a mean number of sources. They're distributed by Poisson. What's the distribution of this H square in the sky? If there's a bunch of Poisson sources, each of which with a certain luminosity function. These can all be computed by hand pretty much, and it's related to confusion, limit type calculation. Everybody that has, yeah.
So can I ask a question about this?
Yes.
That we were talking about adjusting the overall power by, say, changing the mass of the black holes.
Yes.
But presumably they could be at a higher density but a lower contribution mass, right?
Yes.
So is that where this comes in? Is that you're sort of weighing? Do you have fewer big black holes
Yes.
or more small ones?
Yes, exactly.
Okay.
This is
Okay.
by looking. What I will try to convince you is that by looking at this distribution, one can try to start to say
Amazing.
that.
Okay.
Even though, if you look at this, okay, first of all, you would say the measurement itself is not particularly very tight, right? If you look at these error bars, the log, huge. So what are you going to say? Yes, true. However, it's a little bit somehow more interesting than that. But so it already, I can say that it's already meaningful. Those measurements are already meaningful. So okay, because you can do this by hand, and if or some integrals to do this, not a big deal. And if this mass function of black holes, or not mass function, luminosity meaning in gravitational waves, right? Of the black holes is a power law. The whole thing can be done by hand, and the power law, given the error bars there, is pretty good also. The question is what slope of the power law, but okay. But let me say that you also do Monte Carlos with the mass function and everything. So this is results for the distribution of power at a few frequencies that you might expect, either from some Monte Carlo, from just doing it by hand, and you will see that they agree pretty well. And what is it that you see in this plot? You see two things. You see some distributions that are different at different frequencies. I will tell you more how you go, how this, what frequency. I will tell you in a minute. But if you just take a look, these distributions look different, different frequencies. They have a tail, a power law tail, and some sort of Gaussian type bump, okay? With some rescaling, they all fall on top of each other, and I can tell you exactly what those rescalings are and what's the shape. And roughly speaking, what's happening is the following. This tail is given by the chance of having a very bright object. So this is the exact same shape of the luminosity function for one black hole, for one binary. So on the tail, it's just the chances that you see a very bright one. The Gaussian bump is the one that comes from the very numerous but wimpier sources. So if you take the luminosity function and cut it to the place where there's one source above, one source below, the one source above, the amplitudes for which there's only one source above is what's giving this, and then you can compute from the ones that are very numerous, you can compute a mean and a variance, and it will give you this. So that's how you would get a very nice estimate of these. Another thing to look here is this dashed line that's over here. That's the mean, or this one, and this one is for each of the distributions. It's the mean. The thing that I told you was computed and is this f to the minus 4/3 power from Newtonian thing. That's this, the mean of this distribution. This, however, is the peak. The other one is the peak of this. And big difference, right? So that mean is not at all, many times, for astrophysically interesting situations, the most likely thing that you would observe. You might get lucky and get here, and even there's many times which you will get a very bright source to compensate for the fact that most of the time, in this frequency beam, for example, you would observe much less power than the mean, right? And these are all for frequencies and the mass function in the PTA band. So it's not like an exaggeration. Okay, you can estimate all of these pretty much by hand. this is another way of looking at the same thing. This is for some different choices of this mass function to try to get to that background. The peak was what I showed you before. The contribution here is for the average. If you integrate this curve in this axis, you get the average power, okay? And it peaks at some value very much related to the peak in the mass that I showed you before. The dot here is the strain above which, in reality, there's only one source, right? So you can see that for many of these choices that, again, are of interest, most of this average is coming from places where there's much fewer than one source. And this is the reason why, when you look at the typical distribution, the peak is much different than the average. Okay?
So, Matias,
Yeah.
if there is only one source, it should be highly anisotropic.
Yes.
And you should be able to tell that it's
Yes.
one wave coming.
Yes. Yes. People do search for this. At the moment, they haven't been. The data is consistent with not having found any one source. But it turns out that that before you see, you can a little bit see it here. So before you see the one bright source, the first thing that you should notice is that your power, the typical power that you get, is much below the average. So that's where the constraint is actually, that I will show later, coming from. So given that you know, the mass function of these black holes, the contribution from black holes of different mass has a peak. There is a parameter that you can define that in the end captures most of what's going on, which is for a given frequency band, let's compute the average HC square there in the top is the average background that you should, the one that follows this f to the minus 4/3 power. And in the denominator, I have the strain of the most likely source, the source whose mass contributes the most. Right? So this is some estimate of the typical number of sources that are contributing to the background. And if you do that, you will find, because all of these you can do by hand, you can see how that typical number of sources scale with the various properties, the abundance of black holes, the typical mass that of the peak contribution, which is related to the break in the black hole mass function, or the frequency that you're observing. And what I want to show you in this, or here, is if you normalize to the actual observed background as opposed to the, so this is the observed background by nanograph. But the important thing to notice here is that this number of typical number of sources that is contributed, this NC, is of order 1, and it scales for frequencies and masses that are of interest here, but also have very high powers, both in the mass and in the frequency. So as you change the frequency in the pulsar timing array from periods of 1 year to 10 years, this changes by a lot. And also, if you're wondering what black hole contributes the most, if you say from 10 to the 9 or 10 to the 10, also changes by a lot. And this is the distribution of the power that I was showing you before. If you compute, this is the parameter that changes the most, and let's just compute for various values of this power. You can see the shape changes dramatically. So you go, when you have a lot of sources, you go from the peak and the average. Here, I've renormalized all of these distributions so that the average is always 1. And so, because you can rescale the frequencies, all frequencies, all models, they fall into this family with just this one parameter. And so, if this NC number is very big, the peak of the distribution and the mean sit on top of each other. When NC is very small, there's a huge, many orders of magnitude difference. Okay. And here is an example of, so as I was saying, you can rescale everything, and these are just the mass function of black holes in terms of this NC and some more or less universal function you also define the strain not in, like, you divide it by the strain of this peak contribution. And so then if you do it like that, all of these mass functions, they fall on top of each other. These are different choices for the galaxy mass function, scatter in the M-sigma relation, frequencies, a lot of changes. But this is pretty, compared to the error bars, these differences in these curves are not very meaningful. What's more important is that this NC changes by many orders of magnitude. So, okay, so this I already told you. So this is, so this, for example, as you change the peak, the mass that contributes the most to the background in the model, in some meaningfully interesting range. This is this value NC, how it changes for, two frequencies, like period of 10 years and 1 year. Okay, this is kind of the PTA band where we have the measurements, and you can see that for the masses that we are interested in, you go from NCs that are below 1 to NCs that are above 1, and not by a small factor. Okay, big factor. This changes the distribution by quite a bit. And so here, in this plot, this is the ratio between this mean, the mean value of HC squared, the power that for the background that scales with this f to the minus 4/3, divided by the most, the other way around, the most likely, just to get a sense. So the most likely value divided by the mean, okay? As just for, as I change the mass of the black hole that contributes the most, this is the PTA band, if it's 1, it means that you are in a situation in which the peak and the most likely value are on top of each other. If they're very different, you're in this situation. Okay? And so you can see that this is not a small thing; it's a log. And so for heavy things, there's quite a bit of a difference that you should observe in the typical value of the power that you see compared to this prediction of the 4/3 that is realized if most of the contribution comes from lighter black holes that are more numerous. Okay, then you're about around 1. So even though the error bars are pretty big, you can still, this effect is also pretty large, here, there are many ways in which you can show the constraints. One way of parameterizing the whole thing is to ask the question, the number of black holes may be as parameterized by, the total number of black holes as parameters by the mass density in black holes in the local universe. That just gives you a normalization. And then by changing the shape of the mass function of black holes, what's the one that contributes the most, the peak contribution? This is what you expect from the M-sigma relation, okay, for these values, for the fit from the M-sigma relation. This line here is the constraint, and this degeneracy here is just when I match the amplitude, okay? So if I live in this line, I match the measured amplitude of the background, okay? But the fact that we see these first 4 points and we don't see so much of a change in the slope fits this f to the 4/3 is a reasonably good fit, means that the very massive peaks are not so is not what that data likes. It likes lower mass black holes, more numerous. Okay, all with a grain of salt, right? Because this should be done by the professional people of the PTA. But I'm just saying that you can compute the prediction, the distribution of the power, but very robustly. It's a one-parameter model. You should, and there's quite a bit of information with the typical size of error bars that we have now. And if you take it at face value, it points to the fact that the typical counts of black holes are somehow underestimated, not by saying that we should have a few heavier black holes that are contributing, but by having quite a few more lower mass ones. It's not as small. It's not as small. Now, can we have 10 times the mass density in black holes floating around because of the kicks at 10 to the 8 or 10 to the 9 solar masses that you would count with the M sigma relation? That's an interesting question. I haven't tried to. I don't have an opinion. But, okay, so let me jump. Last thing I wanted to say. Very fast, because this is also just some little exercise, but you might ask the question, okay, these black holes that we see were quasars in the past. We have the luminosity function of quasars. They're powered by accretion, so we can try to convert this you all know much better than me. Convert this luminosity into some mass and get an estimate of the mass density of black holes. And people have done that. What's the relation between these things? Okay, so Eddington ratio and so on. So let me just let me just and people have estimated this Eddington ratio in various ways. I don't know. You probably have an opinion. Typically, if you download some Sloan catalog that gives you, through various scaling relations, etc., masses of black holes, volumetric luminosities, you get some blob here which corresponds to these Eddington ratios around point something. Okay, what can we say something about these Eddington ratios from this estimate of the background from gravitational waves? And the thing to say is the following. For these very heavy black holes, a good picture to have in mind is that they accreted in the form of the quasars. They build their mass up to some redshift 2, let's say, but most of the mergers that are producing the gravitational waves happen later on, around redshift 1 or later. Okay, so you can do it, try to solve some equation that have two things at the same time, but if you simple-minded, that gives the same answer pretty much. Let's just take the fact, let's say there's a period of accretion that we can track with the luminosity function of quasars at high redshift. This gives us, if we knew some Eddington ratio, this would give us some sort of mass function of black holes at this point, and then they merge, and this changes the masses of the black holes. Because they merge. And the simple thing is the following. So if they merge and they list to have merged at least once or twice with somebody of similar mass, they started having a mass which is a factor of 2 or 3 or 4 lower than what it is today in the M sigma relation that we measured today. So if you have some value for the Eddington ratio that is good to fit from quasars, just the mass function today, in reality, the actual number that you should get that you would get if you include these mergers for the Eddington ratio is a factor of a few, 3, 4, something like that, higher than that number. And so when people do, so this is an example. This is local mass function again of black holes multiplied by m. And so this is the current one, and this is, you know, if you, this exercise have been done by a long time. So typical number that people get to fit this local black hole mass function requires an Eddington ratio of around 0.2, something like that, which looks reasonable with these other counterparts. This is the average, right? This doesn't mean that there are no quasars with a much higher one, much lower one, but the one that, the average number should be like this, something like this. However, the mass function prior, if you wanted to fit the background, the mass function prior to the mergers is not this one, but this one like this. And so in order to go through, you really need a Eddington ratio a little bit higher than that. Or I don't know. So that's kind of a robust thing. This is telling you how the mass, we don't know the number of mergers, and the background here as a function of the number of mergers is this thing that can change by some sort of factor of 2 that I was telling you. But the more mergers you put in, the initial mass of this black hole is larger than the final one that we observe in the M-sigma relation. And this is examples if all the masses, if all the mergers are equal mass, or if they are distributed in some way, which, so just to see that there's not that much of a difference. You need to, in order to get to the background, the mass of the black holes in the MC, before they merge, they were 10 times or a few, let's say, maybe 8 times smaller than they are today, because they had to merge a couple of times in order to get to the background. So by that factor, you need to increase the Eddington ratio, and I think for people that study this, and I think might be an interesting thing. Okay, so I think I went over, I'm sorry. Okay, so summary, I think there's a nice connection that's pretty model independent between the local population of black holes and the background. You can do these estimates relatively straightforwardly, so there's not much room for hiding. I think it's very interesting that there is quite a bit dependence on there's quite a bit of information in the dependence of the measurement with the frequency, which I think will get better, and I think it would be interesting to include the, rather than just always fitting F to the, the mean thing, just use this simple model, which is a one-parameter model, and I think it really connects to the astrophysics that we can be interested in, I think that's about it.
All right, time for questions.
So Matias, if we take, let's imagine a scenario where indeed astrophysics cannot give the signal they see. There are two possibilities. One, the PTA claim is incorrect. They had some issue. They saw some other sources. Second is, in cosmology, there might be another source. Can you elaborate on the second one? Because the first one is much more messy, but
yes.
The second one, what kind of cosmological sources can produce this background?
Interesting, yes. Okay, let me just say that I am a conservative person. Okay, so blah, 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 no. I mean, if we are within a factor of 2, okay. But anyway, I will entertain. So I think I mean, if you had to say the background measured is off by a little bit, M-sigma relation is off by a little bit, counting all that, all of these, right? So this is one. However, what are the astrophysical backgrounds, or non-astrophysical, but cosmological backgrounds? I think you can think of, for example, some sort of phase transition in the early universe. You can also think at situations in which the power in the fluctuations that lead to structure formation has some sort of bump that leads to the formation of primordial black holes, for example. And this same bump produces also a background of gravitational waves at second order in perturbation theory. People have computed that. Now, all of these things have in common that the shape of the spectrum is not the same at all. Now, we only observed 1 decade. and so with not so large error bars, and so you can tune things so that you are okay trying to explain the background in this way. And I think, on the other hand, that but the situation is that when you do that, if you were to extrapolate that background, which is more of a scale invariant type thing over frequencies significant, a couple of decades more than the PTA on either side, then you would have an omega in gravitational background that is inconsistent with, say, constraints from the effective number of neutrinos that people have. So you really need to tune the thing and make, but okay, it may be possible to do. What I think is not something that will ever happen for these backgrounds is that they produce such a large frequency variation, with this kind of shape over this very small background. So if rather than being supernumerous sources, okay, in that case, the mean is what it is. But if you're really dominated by things that have, are a little bit heavier, this is even more difficult probably to match with some sort of other mechanism. But I think, as the PTA measurements become more robust, I think the frequency information will tell us.
Ramesh, can go ahead. Go ahead.
Okay, so the M sigma,
Yes.
there have been all these murmurs that near the upper mass end, it's actually kind of rises
Yes.
more than people think. There are kind of overmassive
Yes.
black holes. So has that already been included in your set of models?
Yes.
Or is there something you can do?
So in fact, we had 2 papers so far about this. In the first one, we just did the background. And that was our most reasonable explanation. Because if, with the fiducial mass function, most of the contribution comes from black holes of, few times 10 to the 9, right? So, and the contribution goes like the mass to the 5/3. So if I want to explain 4 times more energy with 10 to the 8, I really need to say that I'm missing 10 times more black. That sounds, astronomers make mistakes, but come on, no, not that. So most probably, I just need a few heavy ones and the M sigma relation. So that was, and we had such a break there, you can explain it. However, those guys are so rare that they produce,
They are in your
in the second
cover.
paper, in a sense, when we managed to compute the background, we got killed by this, right? So this would be, say, let me put, just a couple, like order 1 more, like twice as much black holes, but they're a little bit heavier, that they are here. But it doesn't like it because it's, at least at face value with the points that are already there. This big change in the amplitude seems not to be there. So it prefers to put many more early days.
Right.
But I think it's kind of interesting.
Right, but if you say that, it is these bigger massive black holes, and there's just one guy in the sky that is doing producing
Yes.
all the signal, you say that is not yet ruled out, right? People have not.
It is ruled out.
No,
It
it's
is
kind
a
of
single frequency.
a single
well, in each one,
glass.
okay, in which frequency, right? So,
I would say 3
each
years.
frequency would have a 1 black hole there, right? Or how many? So for each frequency bin, there's a set of black holes that are there, okay? So perhaps in some of them, they are just you're dominated by these very rare. But the thing is, you have several bins, and this very rare is very rare, right? So once you get to this 10 to the 9, you are really, it's one of these more extreme distribution. Okay, I have to go with the whole thing, sorry. I don't remember where it is. So, the very rare and the typical value are quite different. So it doesn't really like this so much. You could think, if I look at there is this point over here which is kind of high even, and so people have thought maybe this one is, and they tried, and there's a clear signal of this eventually, which is if you have small enough error bars, that is the pattern of the time delays is not uniform across the direction of the pulse. It is a very distinct pattern. So if there's one over there, most of the, I think I didn't put the slide, but you can tell. So they try to find, is there a location where I can put a very bright source? And unfortunately, with the error bars, it's not, there's no evidence. I don't think there's evidence against it, but there's no evidence.
That was my question, yeah. So maybe, we're just
Yes.
lucky and found a
But
strong guy, but it will be ruled out soon.
Yes, probably, yes. But one thing that for me now is the more clear, because also you can estimate the more clear thing is that before you see a very bright one, you will see much a big shape change here. That happens way before. In fact, I think I didn't put it, but in the paper we estimated the chances that there will be a very bright source that will be, say, as bright as the whole background. And even for the most dramatic things that we had, the chances are very small anyhow. So you don't expect at the current thing one very bright. But
So what if you go the other way and it's a lot of 10 to the 8 solar mass black holes,
Yes.
or 8 point something? How does that compare to like the density of elliptical galaxies or that sort of thing? Like, do you need lots per
yes,
luminous galaxy kind of thing?
Yes, I think that, to me, that is because even, let's see if I can find this plot. So if you look here, this is with the fiducial numbers, right?
Right.
And this is here. So there is already an order of magnitude, which gets more as a, this
As you go
is
down,
because of the m to the 5 there, it goes up, right?
Yeah.
You guys know better than me, but like 10 times more sounds like too much. I mean, it's true, they emerge, they get a kick, if they have spin, they might get ejected. I didn't do the exercise, I think, but it's quite. Also, let's say that before all of this, the people doing the Sultan argument with some relative efficiency that made sense, they were all happy, right? They were getting a rho that was matching density of black holes that was with relative efficiency. Everything was kind of nice, right? The connection with the quasars. Now you're putting 10 times more energy density. Okay, maybe, I don't know, it's accrued in a different way. I don't know, Ramesh can tell me, I'm not sure. Maybe it's possible. But, okay, something you will pay some, I think it's a kind of an interesting part.
Yeah, for sure. And I guess I was asking about ellipticals in particular because presumably they're a reflection of galaxies merging, and like you can ask if there's one black hole per galaxy.
Yes.
What that tells
Okay,
you.
so
Because it like messes up the stars along the way.
yes,
sort of.
yes. I think it might be nice to make some sort of plot which tries to give, if you did like this, compare this, the number density to some, I'll try to produce such a plot. See if I can put some idea in there.
But it's probably close to the fiducial because you sort of assume that every elliptical has a black hole.
Yeah. So here you will need to have many more black holes,
Yeah.
but I mean, you can always try to go to more numerous galaxies, things that are.
Yeah.
Another option is that you have 10. Yeah, I don't know. You have to put them in very numerous things.
Yeah.
Right? So,
Yeah.
and by the time you are around in this region, you're not in the exponential part of the mass function anymore, right? Of the galaxy. So, there is a slope there, but they're getting more numerous, but it's not the dramatic part.
Yeah.
I don't know.
I have a quick question. So are there any discussions about possible systematic errors in the PTA measurement.
Yes, lots. Yes, and in fact, for these high points, there's some issue with effects of propagation effects in the plasma along the way that people complain about.
Also asteroids.
Yes, also asteroids. Yeah, there might be other. Yes, also, you know, the first point is kind of low. You know. Yes, yes. I think there will be a joint analysis of all the PTAs, not in the not so distant future, with all of the data together. Maybe there we will see a more detailed analysis of comparison. And they are doing things slightly different, each of these groups, so maybe by the moment they're trying to get everything together, they have a better sense of, you know, maybe some overestimation of these. Yeah, I think, but the M sigma, yes, it's possible, but the local measurements are not so free from issues, right? So, like for example, so this is a paper Chang-Pei put out after these papers that we had. And she is saying, okay, I'm re-estimating the background, the masses and so on, not based on the M sigma relation, but M bulge, M black hole relation, and not by even changing that, but by claiming there are 10 times more galaxies than people. So, because when I try to count galaxies in the aperture, blah, blah, I don't know, some observational thing. And, okay, so also in the local universe, there's some, and I think the very heavy, I think how many of these, yeah, could the M sigma relation be changing with environment quite a bit? We see, I think a lot of the very heavy galaxies in the M sigma relation are in
Clusters.
coma cluster or something like this. So they're all, maybe they're all together in something, and once we look somewhere else, different story, lots of questions. But that's interesting.
Matias, there is an inconsistency that I've always worried about in this problem. Why do we see so few binary AGMs? There's only about 3 or 4.
Yes.
And now with JW, we're getting out to, you know, much larger redshifts, and I haven't heard any new ones being discovered. So is that density consistent with PTA models? And the other
I haven't
question,
tried to, I understand that.
there's another part to the story, I would think, that if you take into account the massive black holes formed early in the universe from top 3 stars, has that been included in the modeling?
Yeah, I think
That's a very different population to start from.
yes. That's why I like to do it not forward more from the beginning, trying to estimate the number of mergers, because all of this seems to me, it looks like you have a lot of freedom, right? But once you start with the final black, as long as these black holes are part of the things that we are counting locally, then there's not much room for anything, some sort of factor of 2. I think that's how I try to, so as long as they are here now, and they are part of what's being counted in the M sigma relation, those heavy black holes, this is, they are included here. If they are floating around because they're not in the centers of galaxies, they are not here. Yeah, that's the, but you need the estimate of how many are outside the ones we counted is this estimate. So, you know, that's what you have to do. You have to say that they are not in the centers of the galaxies.
Let's, no questions. Let's thank Matias again for nice talk. Matias will also give a launching talk very soon.
Yeah, no worries. Nice to see you. Yeah, yeah, yeah.